Okay, so this meeting is being recorded. Hello everyone. Let me see if oh no, I don't have some. Okay, never mind. Hello everyone. My name is Negar and I'm a PhD student at University of Waterloo. Um, right now I'm doing also an internship in Google, and today I'm going to talk about a topic which is also very sensitive: gender fairness or gender bias in information retrieval systems. um, I was mentoring a master's student at Ryerson University whose thesis was on this topic, and we had a bunch of papers in CIGIR, CIKM, ECIR on this topic, and also we did a tutorial recently in Madrid in CIGIR on this topic. So I have some of the slides from the tutorial papers. I want to point out to different potential works that we can do on this topic, or like the literature. And I know that the topic is a little bit sensitive, so please feel free to interrupt me whenever you want or you have a question, because like if it's become more interactive, it will be also more interesting. Okay, and because now I'm on the Chrome OS, I can't see you. So if you have any questions, Rebecca, or like if there is any message on the chat, please read it for me because I don't see anyone now. Okay, so Esther, I want to start with talking about stereotypical gender biases. And stereotypical gender biases has always been there in the society, starting from many, many years ago, where like due to many reasons, for example, men used to go to hunting, women used to stay in the cave, taking care of children and other stuff. And because of historical thing and many other reasons, they initiated the stereotypical gender biases initiated. But now that it has been many years past and everything has changed, they're still there, and they are having negative impacts on the way we think about the world and problems and many other stuff. For example, we can see the impact in terms of diversity. Last year, Guardian reported that only 15% of AI researchers at Facebook and 10% of AI researchers at Google are women. And this is one of the negative impacts of a stereotypical gender biases that shows up in diversity. Or in another interesting study, the gender gap tracker study in media, they compared the sources of news that were reported by male and female reporters in Canadian news. And apparently the news that were reported by male reporters is 3 times more than female reporters. So if we think about where are we getting the information, this could potentially tells us something. And these stereotypical gender biases do not limit to only society. They also has been mitigated to AI and intelligent systems that we work with. For example, if you search on Bing how to become a police officer, you get the images that include mostly men. Or even in image generation systems that have been developed more recently, if you search for police officer, you see images that almost look like men. And vice versa, we have these stereotypical biases for female. And for example, if you search for how to become a nurse in both search engine and image generation systems, you see mostly images that includes female as a nurse. So if we go like in more researchy stuff, for example, in natural language processing and language models. Sorry?
Oh,
Okay.
good. Someone unmuted themselves by
Okay.
It's fine.
Sorry, because I don't see anyone. It's weird, but okay. So, for example, the sentence "he is a doctor" has a higher conditional likelihood and probability than the sentence "she is a doctor." Or like this was a very famous example, which is from the paper "Man is to computer programmer as woman is to homemaker," and this was one of the first work that investigated these biases across embeddings. So they say that the analogy between man to woman is same as analogy between computer programmer to homemaker. And we see that the bias is also mitigated to word embeddings and so on. So how does if like AI based systems are including such biases, how does that have negative impacts in the society? Imagine like last week, as Harlan was saying, last week he was talking about a recommender system that suggests like well-paid job where to men more than women, or like some similar examples. Imagine an AI-based system that filters resume or like recommend jobs to different users. So these biases will be transferred into such a systems, and then we will see the existing biases being intensified. We will see lack of diversity, or like discrimination against many minority groups, and it will cause us to make prejudice judgments. So if you want to talk more specifically about gender bias in IR, and we want to today narrow it down to how these gender biases, if they exist in current state of the art information retrieval systems, and how we can, we should think about how we can quantify them first, because if we cannot measure something, we cannot improve it. And then we want to see if we can find the source of such a biases, and then lastly, if we can mitigate those. So before I jump into the more detailed stuff, I need to go through some preliminaries, because I'm going to keep saying gendered queries and neutral queries. So we need to make sure that we are on the same page. So in this topic, we usually talk about gendered queries and neutral queries. So as it might be very obvious, gendered queries are those that explicitly include gender-related terms such as men, women, boy, girl, male, female, or like point to male or female celebrity, or like terms like pregnancy that implicitly targets a specific gender. And neutral queries are those that inquire information about non-gendered information need, right? And we are going to talk about a fair ranker. So ideally, we are going to define the fair ranker as a ranker that provides a balanced representation of the protected attributes such as gender, race, ethnicity, age, and etc. And we define a fair ranker based on neutral queries. This is an important point, because we are not talking about gendered queries, because obviously if your query is gendered, we expect that the retrieved results are inclined towards that gender, right? But if we have a neutral query, we expect the retrieved documents, first of all, to be relevant, but at the same time, do not show any inclination towards a specific gender. And if we have two same, like equally relevant documents to the query, the one that with lower degree of gender, we prefer that to be ranked higher. So that is a fair ranker. But how to quantify the bias of the retrieved items? So when we say lower degree of gender biases, we should be able to first quantify that, right? So if you want to quantify the bias of retrieval system, we'll start from measuring the genderedness of a single document. Then we aggregate that bias to the ranked list, and then we aggregate on the ranked list generated from a retrieval system to obtain the bias of the retrieval model. So let's start with how do we measure genderedness of a single document. So mostly currently available gender bias measures, they measure the magnitude of genderedness of each document based on frequency of gendered terms. So mostly they work based on a predefined list of terms, including, like, as you can see, she, woman, her, or like he, man, him, etc. And then they they have lots of details. I don't want to go through the gender metrics in this work, but imagine that there is some function of difference between frequency of male related terms in the retrieved items versus female related term in retrieved items. So this frequency could be like, I don't know, based on term frequency, some exponential function of those, and so on. But the idea is the difference between frequency of the male related entities and female related entities. So once we are able to quantify the genderedness of a single document, we can easily, if we have a ranked list, we can easily measure bias of every single document in the ranked list. Like here we have 8 documents, we measure bias of each single one, and then we can aggregate somehow on those. For example, the simplest way would be to get the average on the list, but also we could do like weighted average to consider the rank, like if a biased document is ranked at the first versus if it ranked at 10th, it won't be the same, right? So we want the biased documents to be ranked as low as possible. So we could do also weighted average or some other stuff. And then once we have the bias of the list of retrieved results, then we can aggregate it on a query set and retrieve results of a set of queries to get the bias of the retrieval system. Once we have the bias of the retrieval system and we have two different systems, we can say, okay, this retrieval system has less bias than the other one, right? There are also other metrics such as NFAIR. I don't want to go to details of that, but as you might be all familiar with NDCG, I just wanted to point out that there are some metrics such as NDCG, which is called NFAIR, and they exactly like NDCG, but they have also a soft threshold. For example, they won't say if there is a single male-related term in this document, we should consider that as gendered inclined document. But they have the threshold that, okay, if a document has more than, or the difference between female-related and male-related terms in this document is more than a certain threshold, then we say that this document has inclination toward male. Or like they consider the ideal situation of the fair rank list. So for example, if you have a pool of 10 documents and they are all somehow biased, we consider the ideal ranking of those. What is the ideal based on whatever that we have, and then compare current level of biases with respect to ideal situation. Not that we always want unbiased documents. If we don't have them, it's okay. From the set of documents that we are working with, we consider ideal situation and we compare the current retrieve rank list with respect to ideal situation. But the takeaway is that we have several gender bias quantifiers that all works based on frequency of gender terms, but some of them has soft threshold, some of them has hard threshold, and so on and so forth. Okay, so these gender bias studies in information retrieval started with very interesting Negar 2020 paper, which is called Do Neural Ranking Models Intensify Gender Biases? So in this study, they compared the level of gender bias in retrieved items by BM25, like sparse retriever, well-known sparse retrieval versus neural rankers. And what they did is that, let's say this y-axis here is ARB, which is one of those gender bias metrics, right? So the higher means that the results are more biased toward male. And then we have the results of different neural rankers. The red one is BM25, and the rest are all neural rankers that has been trained on MS Marco datasets. And as I said, the higher bars means that the results are more biased toward male. And again, I want to mention that all these results are on neutral queries, so that we have a subset of MS Marco. They've been annotated by Amazon mTorx as neutral queries. This means that they do not have any information about any genders, and we expect the results also to not be inclined towards male, right? But as you can see, all the neural rankers that has been trained on some training data sets has intensified gender biases, and the level of biases in all of them are more than BM25, right? So we have like, if you see the birth-based neural rankers, the yellow one, and compare it to a red one in different cutoff of ranking, like in top 5, in top 10, in top 20, it has significantly more level of biases. So the answer to this question is actually yes, and neural rankers intensify gender biases toward male inclination more than unsupervised rankers, like BM25. But we should think about what could be the potential source of these biases. Why neural rankers intensify biases compared to unsupervised ranker? So in this study, we were thinking about because neural rankers have been trained on some sets of relevance judgments and some training set, maybe that training set is already imposed with biases, and that's why neural rankers are biased more than unsupervised one. So we are willing to study, like in this study, we wanted to study if, to what extent gender biases may be presented in relevance judgment collection. So what do we want to do is that we want to, like, by relevance judgments, if you know, I mean, the QRLs. So for each query, there were some documents that were annotated as the relevant document for the query, right? So what we wanted to do was to compare the relevant judgments for queries that were annotated as female versus relevant judgments that were annotated for male. Do they differ in terms of their characteristics, or like we want to compare them? But before that, because we have a huge collection of queries, we are not able to annotate every single query in MS Marco dataset manually. So that's why we need the query gender identifier or query gender classifier. So we have this fine-tuned BERT on some human annotated query sets, like it's around 3,400 queries that were annotated as neutral, female, and male from the Do Neural Rankers Intensify gender biases paper that we just talked about. And then BERT is fine-tuned on that with a classification layer to predict the gender of the query. For example, when did Copernicus leave, is annotated as male class, and then this classifier also shows relatively very high accuracy and a fun score, and that's the current state-of-the-art query gender classifier. And here we can see more examples. For example, if you talk about pregnancy, the classifier will predict the gender of the query as female, or if you talk about a female celebrity, or if you talk about male celebrity, or if you talk about a neutral query such as average percentage of accepted scholarships, it will predict the gender of the query as neutral. So now what do we have? Now we have different subsets of query that is annotated as male, female, and neutral. And all of these queries has a relevant judge document. Now we want to see what are the characteristics of relevant judge documents for male query sets versus female query sets versus the neutral query sets. But this time you want to go beyond the gender terms, because that gender terms that I showed you earlier is very limited, and like maybe there are like 400 gender terms in each group, like female related and male related. But here we use the Luke toolkit or LIWC toolkit, which is a linguistic inquiry and word count toolkit. It's like a psychological based library. It's a very famous one, and it's a text analytics toolkit, which gives you a degree of which of these psychological characteristics are included in a piece of text. For example, some of the affective processes such as sadness, anger, anxiety, or like cognitive processes, personal concerns such as work, money, and then personal drives. So given a document, it will give something like a distribution of how much of these categories do exist in that document. So here, these figures are showing the degree of each of these psychological characteristics in female and male relevant judge documents. So, for example, if you look at the negative emotion, we see that the female related, the relevant judge documents for female queries has higher negative emotions compared to male, or even compared to neutral set of queries. Or if you look at anger, we see that female related relevant judge documents has lower degree of anger compared to male. Or the opposite is true for anxiety. And here are other psychological characteristics such as cognitive processes, personal concerns, or drive. Again, for example, for power, we see that the degree of power in relevant judge documents for male queries is much higher than relevant judge documents for female, right? So if we think about those differences, and if we think about the relevant judgments as the primary source for end-to-end training of neural rankers, we have these bias labels that lead to biased models. And also, on the other hand, we are also evaluating such systems and these bias labels. So if these labels include any inclination towards any gender, and if they are biased, bias label cause not only biased models, but also biased evaluation. So, fact one, relevance judgments in information retrieval systems are biased. And the second fact is that neural rankers are trained on those relevance judgments. Therefore, we can say that neural rankers could potentially and implicitly learn these biases from the labels that we have. If we want to have a fair ranker on such labels, first of all, we want the ranker to maintain the retrieval effectiveness, because who wants a ranker that has low performance even though it's not biased, right? But also we want to minimize these biases. So in the next study that I'm going to talk about, we are going to see if we can make neural rankers aware of such a biases. And I'm going to just do some recap. I'm sure you're all familiar with these concepts, but in currently state-of-the-art neural rankers, the two typical architectures for ranking and re-ranking is bi-encoder and cross-encoder, which the idea is that if we have representation of query and documents, we want to minimize the distance of query to its positive label to relevant documents. At the same time, we want to maximize the distance of the query from irrelevant documents or negative ones, right? And this is a very typical hinge loss, which is this, and the same notion is appearing here, which this phi is the scoring function that we have for query and positive documents, and we have also the scoring function for query and negative documents or irrelevant documents. And we want to, as I said, maximize this score between query and relevant documents and minimize the score between query and irrelevant documents, right? So in this bias-aware loss function, we propose that, okay, we can keep the same loss function, but add some regularizers so that we are penalizing the model based on not only irrelevant documents, but also the level of bias. So the model should be penalized if it's seeing a biased document. So first we were thinking, okay, what if we change this function and we add this psi of documents, which is basically the level of genderedness of the documents. So we add a term to the scoring function that penalizes the model if it's biased. But if you are penalizing positive documents because of its being biased, it will it's like a car that it has very fancy seats, but it doesn't have any wheels. Who wants such a car? If the model has low performance, but it's not biased, no one will buy that, right? So and because we don't have mostly these training data sets has very sparse labels, we want to get the most out of the current labels that we have, right? That's why we relax this equation by just penalizing on irrelevant and biased documents. So if a document is relevant, we don't do anything if it's biased or not. Let's keep that term as it is. But if for when we are measuring the scoring function between query and negative documents, we keep the scoring function as well as if that document being biased. So what does this mean? It means that if a document is positive, it's okay, we'll keep that. If a document is negative, and if it's biased, we will penalize it more, right? So I don't want to go into, and what is the intuition behind that? So you might think that why are we penalizing the loss function because of irrelevant documents? Because the users will be exposed to both relevant and irrelevant documents, right? So the users will be exposed to, for example, top 10 documents, maybe one or two of them are relevant, the rest are not relevant, but they are being exposed to. Users are being exposed to them. So if something is even irrelevant, it's better to have the unbiased irrelevant ones up there rather than the biased ones, right? I don't want to go into the details of the results of this model, but I just want to mention that first of all, this model keeps the performance as it is. So these bars here, like the red one is the model that I just explained to you, the one that the loss function is being regularized. And this is the MRR difference between the original model and this model. So the performance has not been dropped significantly, but the bias has been reduced significantly. So I know it might not be very clear, but the main takeaway is that it will keep performance. The performance will not drop significantly, but the bias would be. Yeah, so that was one work on how we can mitigate biases in neural rankers. But there's also another strategy which is simple, but it works very well. Before I jump into this second work, I want to do another recap on how we train the neural rankers usually and their training procedure. So because we don't have negative labels mostly, and we only have positive labels, how we usually train these neural rankers is that we use BM25 retrieved items as weak negative labels. So we retrieve, given a query with BM25, we retrieve top 1,000 documents. We have a list of top 1,000 retrieved documents by BM25. We randomly select some of those that has not been labeled as relevant as negative samples. And then when we are training the model, we need triples of query, positive document, and negative document. So we keep repeating this positive passage. So query, for example, if the D3 is the positive passage, we keep repeating query D3 and one of the randomly selected documents from this list, right? So different studies has shown that how we select those negative samples are very important, and they actually have lots of impact on the performance. For example, you could just randomly select some documents as negative samples. You could use the retrieved results by BM25. You could train a model to select negative samples, and so on and so forth. So there are many ways that you could, and there are many strategies that you could take to select your negative samples. And how we select negative samples has impact on the performance of the model, right? So we were thinking, why not using this negative sampling strategy to reduce the biases of neural ranking models? So our goal is to propose a bias-aware negative sampling strategy. So how do we do that? So let's say we have this query, we have the retrieved documents for the query. We measure the bias of the retrieved documents, right? For example, this is the BM25 results. We measure the bias of each document. For example, these are the bias level of each of these 8 documents. And then we re-rank the list based on their level of biases, not based on the relevance, right? So let's say this ranked list will become like this when you re-rank it based on the level of biases. And then when you want to select the negative samples, you won't just pick random samples from the whole list, but a portion of your negative samples, you can select it from the most biased one. So these documents that are high ranked after re-ranking based on bias are the most biased documents. So a portion of random samples that you select would be based on these biased documents, and a portion could be selected randomly because you don't want the model to learn that all the gender documents are bad and you should avoid them, right? So we have these free parameters that you can like it makes the model flexible to see to how much it should be sensitive to our gender documents. And this simple strategy has some advantages. For example, first of all, it can reduce the biases without dropping the performance, and also there is no change to there is no need to change anything in the loss function or anything. It's just how you select your negative samples, so it won't add any extra computational overhead or something. And we are basically training the model to learn that okay, these negative documents, if a query is neutral, the negative documents should not be even biased, right? So the model will learn to avoid negative and biased documents at the same time. So the goal of learning is not only to learn relevant, but also learn being relevant and fair for neutral queries. And so this is the results of this paper. Uh, the circles are the original models. For example, let's say red one is BERT base. If you use BERT base as a neural rankers, and then if you use this negative sampling strategy, the x-axis is unfair. So the higher is more fair results. And the y-axis is MRR. So we expect that, like in ideal scenario, we want the y-axis to not be changed because we don't want any change in the performance, but we want the x-axis to be as far as possible to the right? So if we have a horizontal arrow, it would be the perfect scenario. So as you can see, all these models, the bias level has been decreased, so the fairness has been increased, and they're being pushed to the right, but the performance has not been dropped significantly. For example, if you see going from this one to this one, the difference in y-axis would be how much the performance has been dropped, and the difference in x-axis is how much the fairness have been increased. And here is just one example of if you do such a bias-aware negative sampling strategy when you are training your neural rankers, what would happen? For example, we have how important is a governor, right? If you have such a query, we don't want the documents, the retrieved documents, to refer to governor as he, right? Or like, is a supervisor considered a manager? For this query also, we don't want the results to refer to he or men, right? So this is not a good option for such a query that would consider it as neutral. So in original ranking, we see that this document has been positioned in second, but after the model has been trained with this deep bias-aware strategy, this document, which is not pleasant for us, has been ranked 88. So we've been pushing this down, but the relevant documents has stayed the same rank. Okay, so I talked about two strategies that we can train neural rankers with gender bias and make them more fair. But what are really the limitations? How reliable these metrics are? Are we really quantifying the level of gender biases in this document reliably? And also, like, it's very simple to quantify bias of the retrieved result just based on the frequency of male-related and female-related terms. It's very convenient, but how much it's reliable and how much it's generalizable? So in another work, we studied characteristics of these gender biases, how consistent they are, how reliable they are. So let's say we have the three mostly widely used gender bias quantifiers, and I don't want to go into details of that study, but I want to give the findings of those studies because I think it's very important. We find out, based on some experiments that we ran, that these gender bias quantifiers that currently exist, they don't even necessarily are consistent with each other. So one of the metrics might say that this document is less biased than the other one, and the other one disagree with that. So the consistency level is not that high, and so it's not that generalizable, and also they are very sensitive to that predefined list of terms that we have. So we manipulated those lists, and we have different perturbation of the list by removing some of the terms or adding some of the terms. And we noted that once you change that predefined list of terms, because the whole metric is working based on that, the range of the outcome of the evaluation, the quantifiers, the gender bias measures will varies, and it will mess up with everything. So they are very sensitive, and the results are not even consistent with each other. Other limitations of these works is that definitely definitely it's one of the most important limitations, that the gender has been defined as binary attribute. We don't have any data on multiple gender. Like, for example, one of the data sets that they asked human to annotate them, out of, like, let's say 4,000 queries, only about 40 of them has been annotated as multiple gender. So we don't have enough data to study gender beyond binary definition. And there are not many data available, and sometimes annotating for this task is very subjective. All these limitations will help us for the future work, and also all these methods that works with, like, reducing gender biases could be potentially expanded to other sensitive attributes such as ethnicity, race, or other stuff. So what we covered today was, first of all, we went high level into definition of like how we define gender bias in our information retrieval system, how we quantify them, and how do we identify gender biases in neural rankers. And the main takeaway from this part was that neural rankers has intensified biases compared to sparse retrievers such as BM25. And also, one of the potential source of these biases are the relevance judgments and the training set that those neural rankers has been trained on. We went through idea of 2D biasing approach for retrieval methods, one through loss function, through regularizing loss function, and one through training sampling strategies. And the conclusion is that we have both good news and bad news. We have bad news because there are stereotypical biases in the retrieved results of search engines. They've been intensified at scale, and these biases, maybe not intentional, but they've been inherited because of the relevance judgments, or because the rankers has been only optimized for concept of relevance and notion of relevance, not for the fairness. And the good news is it's possible to systematically debias such systems without sacrificing retrieval effectiveness. And we can do that by either changing the architecture of the training, changing the loss function, or even appropriate training strategy. Yeah. Thank you, everyone, for listening to my talk, and a big thanks to all my colleagues that were collaborated on these papers. I would be happy to discuss further with you.
Thank you so much for your presentation. It was really, really interesting. I open the floor to anyone who has questions.
Sorry, can you